Okay, so today we're going to look at how we calculate asymmetry. We're also going to have a little look at how we calculate the direction of asymmetry, and then we're going to go one step further and use a statistical approach in Microsoft Excel called the Kappa coefficient, which looks at how consistent the direction of asymmetry is between test sessions. So the first thing we've got here is single leg counter movement jump scores on left and right for test session 1 and test session 2. Now, first thing we do is we calculate asymmetry of each individual subject here, and we do that by use of a standard percentage difference equation. I think of note as well, it's worth highlighting that if you used an equation such as stronger value minus weaker value divided by stronger value, that would then give you the same outcome as our proposed formula here. So we get our asymmetry values here for our 12 subjects, and then we've got our mean and our standard deviation here as well. And you can see that actually in test session 1 and test session 2, the mean values are a little bit different, but actually they're relatively consistent if we just look at that magnitude of asymmetry. The other thing you can see as well is that the standard deviation of the mean is quite high. So we're up at around about sort of 70 odd percent, 65 to 70%, which shows you that this is quite a variable concept. And actually you can just look at those individual values and see that the first three have got asymmetry scores of 10 and 16%. And then as we move down the list, we've got values as low as 1.3 and values as high as 12.77. So that's how we calculate our asymmetry value. And now we're going to look at how we add the direction of asymmetry. Now, the direction of asymmetry is a concept that I think perhaps might have been first brought about by Franco and Pellizzeri, and more recently by Sean Maloney in some of his research. And it refers to how consistently the asymmetry favors the same limb over test sessions. So what we've done to calculate the direction of asymmetry is we've taken our formula at the top here, and then we've added on something called an if function, which in this example basically says, if the left leg scores higher than the right leg, turn it into a negative value, but don't change the magnitude. And that's something that some limb symmetry index equations have been prone to doing in the past. So in our first subject in test 1, the formula is set up so that because the right limb scored higher than the left, it remains as a positive value. Subject 2, however, you can see that they jump just over 10% higher on their left leg, and as a consequence, once we throw on that if function on the end, we get the values exactly the same as what we worked out in our third column here, but it's just turned it into a negative. And that allows us to calculate the direction of asymmetry for test session 1 and test session 2. Now, if we go to our second tab, what we do is we've copied and pasted in here our direction of asymmetry values, okay? And we've got that for both test sessions. Now, in order to look at the Kappa coefficient, we need to code the data in ones and zeros. Now, the Kappa coefficient is designed to look at the proportion of agreement between two methods once any agreement that has occurred already has been removed by chance. So in this example, what we've done is that any asymmetry value that favors the right leg remains positive, and we've given that a score of 1. And any asymmetry value that favors the left leg, okay, we've given that a score of 0. And what we've done is we've given everyone coded values for asymmetry in test session 1 and test session 2. What we then do is we set up this, I guess it's a small matrix, really. And what we've got here is coded values for session 1, coded values for session 2, and there's a number of steps that we need to take to be able to work out the Kappa coefficient. The first thing we do is we look at how often in test session 1 and test session 2 do they both score 0. So we're looking for a double 0 in our columns here, and you can see that there's one double zero, there's another double zero, there's the third one, and there's the fourth one. So out of 12 subjects, okay, we've got 4 times that we see a double zero. We then do exactly the same process for ones. So if subject number 1 scored a 1 in test session 1, does he also score a 1 in test session 2? And we can see that he does. So there's our first double 1, there's our second double 1, and there's our third and fourth double 1. So we've got 4 times that occurs out of 12. And then we're just looking for every possible combination, okay, of numbers within this matrix. So the next thing to do is every time that you see a 0 in test session 2, how often does test session 1 have a 1? So we can see there's a 0 there and there, but it's consistent. There's a 0 in test session 2, and there's a 1 in test session 1. So there's our first one. That's consistent. That's not. You can see in test session 2, 0. Test session 1 is 1, and that's consistent. So we put a 2 in there, and that gives us a total of 6 subjects in this particular column. We've also then got 2 times when test session 2 scores a 1, but test session 1 scores a 0. And that accounts for our 12 subjects. And if you want to total that up and double check it, you can go 4 plus 2 is 6, 2 plus 4 is 6. So that along this row here, we know that equals 12. We do the same thing on this side. 4 plus 2 equals 6, 2 plus 4 equals 6. And that's how we account for 12 in our column. The next thing we need to do is we need to represent these numbers as a percentage of the total number of subjects that we have. And actually this is an example that's really quite easy because we don't have lots of subjects, and at the same time every number that we see on the outside of our matrix is a 6, which means all our percentages are 50%. So in order to determine our Kappa coefficients, we need to go through a couple of stages before we get there. So stage 1 is where we add together the double zeros and the double ones and look at that as a value or as a percentage or as a ratio of the total number of subjects. Okay, so you can see here that G6 plus G7 plus H7, sorry, is 4 plus 4 divided by 12, and we get a value of 0.67. Stage 2 is a little bit more complex, okay? This is where we take G9, which is our first 50% value, we multiply it by J6, which is our next 50% value, then we add that to H9 and J7. So this is what it looks like here. And essentially what we're doing is we're taking this percentage value, multiplying it by this percentage value, and then we're adding that on to this value multiplied by this value. And because all our percentages are 50% in this particular example, you can see that we come out at 0.5. And then our final stage, our third stage, if you like, to get our Kappa coefficient is as follows. We take 0.67 and we subtract 0.50, and then we divide that by 1 minus stage 2 on 0.50, and you can see the equation just up at the top there. G10 minus G11 divided by 1 minus G11. And when we put that through, we get a Kappa coefficient of 0.33. And here's our suggested scale on the right-hand side, when that falls into the fair bracket. But as you can see, actually, the scale, like a correlation, goes from 0 to 1. 0.33 is not particularly high. What that tells us is that we've got a highly variable number for the direction of asymmetry. And crudely put, what that means is that the direction of asymmetry is very variable. Now, the reason we might want to look at this is because, as I said before, if you look at the mean value of asymmetry in test session 1 and the mean value of asymmetry in test session 2, it's changed a little bit, but actually those values are very, very similar. So practitioners could look at those values and think that from a mean perspective, there isn't really that much to change. And you wouldn't necessarily be concerned with those values because they're not too big, and you probably wouldn't use that data to help make any decisions because the numbers themselves look relatively consistent. However, when we monitor the direction of asymmetry, we see that there's a lot of variability not accounted for here by virtue of having only 0.33 or fair levels of agreement for the direction of asymmetry. The final thing to say, I guess, is that actually this is probably something that's quite an important line of investigation for healthy athletes. So as practitioners, if you're working with your athletes and they're not injured and they've had a very consistent period of training over time, they haven't been injured for a long period of time, and you're well aware of their training and injury history, there's probably no real obvious reason why a between limb deficit would exist. In an injured athlete, there's an obvious reason for that deficit because one side is limited by its ability to perform because of the injury. But in a healthy athlete that's had consistency in training over a period of time, that reason is perhaps less obvious. And if we just use the magnitude or that mean asymmetry value, it's probably not telling us as much as what's going on. So a big thing that we're starting to look into is the direction of asymmetry, how variable that is, and ultimately that's probably something that allows us to understand whether or not asymmetry is being consistent over a period of time in our athletes. And if it is, only then are we able to have a more in-depth understanding as whether or not we can use this as part of the monitoring process.